Perfect. I think we're ready to start. So, welcome, guys. Thank you very much for attending my talk on technical and social attacks against validators and proof-of-stake networks. It is sort of an overview of some of the things you can do when you deal with proof-of-stake networks and validators, and how either you can attack the entire networks or you can attack individual validators in order to eventually get to a network-wide attack. So I'll give you a quick intro so you know where I'm coming from and sort of the context that I'm speaking from. So this is, wait, do I have a pointer? Yeah. Oh, there. Yeah, perfect. So I'm one of the founders of Cryptium Labs. Cryptium Labs was, actually, yeah, I'll come back to this. So I'm one of the founders of Cryptium Labs. I used to be a technologist at Web3 Foundation working on Polkadot. And before that, I was a core developer and head of partnerships at Cosmos/Tendermint. So Cryptium Labs was actually born out of the experience at Cosmos. So in around December 2017, we had a software piece that was sort of in a state where we could start deploying this to testnets. And so what I did in December, I jumped on a Zoom call with 4 other validators at the time, and we set up the first decentralized testnet for Cosmos back then. And so this sort of developed, and over time, by early 2018, it became clear that running validators is actually something extremely interesting and something that's sort of an interesting technical challenge to do. And so that's why we set up Cryptium Labs in order to run secure validation services. And yeah, so I'll give you a little bit of background of what Cryptium Labs actually does. It's technically very simple. So we are a proof-of-stake validation company. We run secure networks. Sort of any reasonable proof-of-stake network we would validate. Currently we're live on Tezos, which went live in June 2018 roughly. We're also live on IrisNet as of like 3 days ago. Cosmos will launch next week, I think. And then there's Adrian and Polkadot and sort of any future reasonable proof-of-stake networks. And so this is really the main thing. But the thing is, while we do validation, one of the problems we discovered is that we didn't want to run protocols that we didn't understand. So like every network that we're launching, we spend a ton of time trying to understand and diving into the code on how these protocols actually implement, how the client implementations work, how the networking stacks work. Which is why we also ended up doing a lot of protocol development, because we are sort of in a position where we learn how the protocols work anyway, so we are perfectly positioned to also then contribute back to them. And so the last point is community development, community education. As a validator, you're sort of this interesting intersection where you interact at a very technical level with the protocol and at a very high level with the users of the protocol. So you're at a very, very nice sweet spot where you can sort of take the technical learnings and explain them to the average user. And yeah, so we're based in Switzerland. This is also not by accident. So we picked Switzerland for very specific reasons, which was mostly its political stability, the very nice feature that it's like not on any geological fault lines, so we aren't in like a hurricane zone. We don't have to expect earthquakes, which makes running a secure, high assurance validator much easier if you don't have to sort of plan around earthquakes hitting San Francisco. And the other cool thing is Switzerland historically has been a very safe place, and the government is extremely friendly towards crypto regulations, which sort of means that instead of having to deal with the regulation that comes top down, we can help the government understand how proof of stake actually works, what validation is, and help them shape regulations around this. So yeah, that's sort of just quick background on where I'm coming from. So today we're going to talk about technical and social attacks against proof-of-stake networks and its validators. I'll start with a brief primer on proof-of-stake and how it works, just so that everyone's on the same page. So in the past, and also currently, we have proof-of-work, which is, generally speaking, extremely wasteful, right? Like the scarce resource you're burning is electricity, and so in order to compete in Bitcoin mining, you have to burn a ton of electricity. Proof of stake is this neat alternative that can provide a similar security guarantee as proof of work while wasting a lot less resources. So the scarce resource in proof of stake is capital. So instead of burning electricity in order to gain hash power, you lock up capital. And that's sort of the opportunity cost there. The other interesting aspect that's like rarely talked about with proof of stake is that it allows us to build more interesting economic models, right? In proof of work, the protocol itself does not have control of the asset that is securing the chain itself. So in proof of work, you sort of have ASICs, but the protocol itself has no notion on how these ASICs work or how these, or can't do anything with these ASICs. In proof of stake, the nice part is that the protocols actually have a notion of what the underlying asset is, so we can design much more complex economic security models around proof of stake. This is also one of the downsides because there's also complexity, but sort of an interesting area that you can look into. Generally speaking, in proof of stake, the networks are only as secure as their validator set, right? If you can compromise a majority, or not even majority, like a third of the validator set of any proof of stake network, you can mostly compromise the entire network. Which is why this talk is a blend of sort of attacks against single validators as well as attacks against entire networks, because an attack against an entire network often starts with an attack against a single validator. Again, so the way this works in proof of stake is you have usually delegators and validators which lock up some capital in order to participate in consensus. There are two main classes of faults. You have safety faults and liveness faults. So safety faults happen when someone equivocates. So if a validator that is allowed to participate in consensus provides a signature for the same block height, but on two different blocks, that's what equivocation means in this sense. And this is a real security risk and extremely dangerous in proof of stake, because in proof of work you have to pick which fork you're building on, right? Like, I have to either decide that I'm going with block A or block B when I decide where to put my hash power. In proof of stake, I don't have this inherent physical limitation. I can theoretically build on all possible forks that I see. And due to that, you can sort of create any history if you didn't have anything at stake. So by making safety faults, so signing two blocks at the same height, slashable, you introduce an opportunity cost there. So that it is not in your best interest anymore to sign every single fork, but rather you have to also pick which fork you're going to build on top. Then the second class of faults is liveness faults, which effectively just means that a validator said he would want to participate in consensus, and when it is his time to participate, that could be in protocols such as Tendermint consensus in every single block, that the validator is not online, not participating in that consensus round, or in protocols like Tezos, where you have like assigned slots where you're allowed to produce blocks as a validator, and so you're offline for that slot. Liveness faults, generally speaking, aren't huge security risks unless a lot of validators go offline at the same time. So if a single validator is offline, that's like not a huge problem. The protocols will do fine. If sort of in Tendermint consensus, if more than a third go offline, that becomes a huge problem because the chain starts halting. If the same thing happens in Tezos, the chain slows down a lot. But generally, safety faults, extremely dangerous to the protocol. Liveness faults, only in large numbers. And so proof of stake is this very general term. And there are sort of different instantiations of proof of stake. And Awa is going to talk about them tomorrow in her talk. But sort of just to give you an overview, there is liquid proof of stake, which is Tezos. There's nominated proof of stake, which is Polkadot. And there's bonded proof of stake, which is Cosmos. They all sound very different. The basic goals are the same, though. All right, technical attacks against validators and proof of stake networks. So generally speaking, when I say technical attacks, I mean attacks that require an in-depth understanding of the underlying client implementations and the underlying protocol implementations in order to execute. They may require an attacker to modify so instead of just running the default code, they will require that an attacker sort of implements their own node or guts in existing client implementations to just do what they wanted to do. And I'll talk about a couple of different classes. In the beginning when I did my slides, I didn't have any sort of subpoints, so we'll run through, I think, 4 or 5 different attacks, or like attack areas. So the first very simple attack area is actually implementation attacks. And under implementation attacks, I also have volumetric DOS attacks, right? And volumetric DOS attacks are extremely easy to defend against. They are sort of simple to pull off. You just need to sort of flooding a server with requests or IP packets. But they're extremely simple to defend against. Sort of, we have 10 years of experience defending normal web services against DOS attacks. And right now, you can effectively just pay Cloudflare $2,000 a month, and Cloudflare will defend against every possible DOS attack on any possible port. If you're only running over HTTP, then Cloudflare doesn't cost any money. But if you sort of want custom ports, then you have to pay them like $1,500, I think. As well, on sort of the implementation side, so this is a lot thinking about what is vulnerable in the client. So we had examples of RPC vulnerabilities where you can not only extract extra information, but you can also cause resource exhaustion on the client. And some clients launched sort of with open to the public RPC endpoints, which took down a bunch of nodes in the Cosmos testnets. On Ethereum, we had this as an even worse case that nodes launched with RPC endpoints opened that if you unlocked your wallet and anyone that could connect to the RPC endpoints could all of a sudden steal the funds out of your wallet. Then there's also the peer-to-peer layer. We've seen, and sort of those attacks are about the fact that can you figure out whether you can send specific requests on the peer-to-peer layer that aren't sort of rate limited in order to start crashing nodes or to start getting nodes into a state where they can't make progress anymore. Like a good example of this could be, can I send unlimited requests to a node on the peer-to-peer layer to ask for other peers? And sort of if I do this too much, is there a file descriptor leak that after some time crashes your node? We've also seen this. Then the next sort of area of attack is mempools. Generally speaking, mempools are quite vulnerable because when a new transaction, an unseen transaction, first hits a mempool, the state machine that sort of runs the protocol has to somehow validate this transaction, right? Is this complete garbage, or is this something that looks reasonable and can potentially actually succeed when executing on the actual network? And so in Tendermint Core land, this is called sort of the check-TX step. So when a transaction comes in, Tendermint Core runs check-TX to check basic validity rules. And sort of a lot of attacks there revolve around, are there transactions which never get committed into the state, but still cause a high computational overhead? Because nodes generally have a really hard time defending against this. And sort of this also goes hand in hand with vulnerabilities around the state machines, where can I send transactions that that exhaust, sort of that don't pay as much gas as the or like that exhaust the computational resources without paying much for it. Sort of early on, actually, one of the interesting things we did at Cosmos was in sort of early 2018, we came up with this architecture for sentry nodes, which is effectively you have a sort of a firewall around your validators so that you're signing the node that actually signs blocks and participates in consensus never goes down, but rather, because it's never connected to any untrusted input in the first place, but is rather connected to a bunch of nodes that you control and that you expose to the public. And if there's a malicious attack against you, those nodes will crash first, but your actual signing server doesn't crash. And so you could sort of construct this in hierarchical tiers where you have like public sentry nodes that everyone can hit, and then you have like private sentry nodes that only a few select people can hit, so that even if all your public nodes get taken down, at least your private sentry nodes still remain up. I will actually talk later about this, why this isn't super necessary at launch unless you're getting attacked. The next interesting area is, and so network analysis, this isn't necessarily an attack in itself, but it's rather an intelligence gathering tool. It allows you to very accurately map how the underlying networking graph of the connection between the nodes in the network looks like. Yeah, so the goal of the network analysis is effectively to map the entire network of nodes and how they're connected to each other. And it is sort of, there are many different ways to do this, and sort of some are more sophisticated than others. So the simplest one is that you build a custom client implementation that only implements a peer-to-peer stack and just very aggressively queries other nodes for the peers they know about, and then you try to connect to those peers and then query them again. So you start establishing a list of all the peers in the network. And moreover, you can sort of, if node A tells me about these peers, I can make the assumption that node A is actually connected to them. So I can sort of weakly draw links between nodes. But it doesn't give me full assurance. Sort of a second type of this that you can use in order to achieve network analysis is to run something like mass scan and try to sort of ping every single, and this is totally possible, by the way, like you can ping every single IP address on the global internet in the IPv4 space in, I think, about 24 hours if you sort of on a 10 gigabit Ethernet card. So you can effectively try to connect to every single IP address in the global IPv4 space on the specific port that your default client implementation uses. By the way, don't do this without talking to your ISP. They get very angry because they get a lot of, like some parts of the address space on the internet do not like getting scanned. So talk to your ISP before you do this. They should be aware because they will get a lot of abuse. And sort of, but the third level, or the third way to do this is actually slightly more sophisticated. It involves use heavily connected node to send transactions. And sort of the basic idea is that this heavily connected node can send a transaction, can send a unique transaction to one of its peers. Then on that peer, it will first enter this sort of check TX phase before it goes into the mempool, which means it maybe spends like a second trying to verify that transaction. And only after a second does it get relayed to other connected peers. So all of a sudden you see these very clear step functions when I send a transaction to node A, and that transaction then takes a second. Then it sends it on to its peer, so to node B, and then node B takes another second. So after 2 seconds, if I'm also connected to node B will gossip that transaction to me. And this is sort of an extremely reliable way to map most of the network graph. And this comes in handy for other kinds of attacks where you sort of want to cluster IP addresses to validators. So you can say sort of validator A is behind these 5 IP addresses. The second type of, again, this isn't in itself an attack. This is a tool that you can build up that you can then leverage into an attack. It's network partitions. So with modern cloud computing environments, it's extremely cheap to sort of spin up hundreds of thousands of nodes. So if you imagine that you are in, maybe at launch, there are 100 actual full nodes in the network. I can, with like 3 clicks on Google Cloud or AWS, launch 900 other full nodes. And all of a sudden, I represent, like, my peers represent a massive majority of the nodes in the network. So I can also then start modifying the client implementation so that my peers will only gossip my own peers to other nodes. So if a new node joins the network and asks, and it only at the beginning of the network, when the node comes up, it only connects to one of my nodes. My node will only tell it other nodes that I also control. So generally speaking, when you start your clients, be very careful on the first couple of nodes you choose because it's a very easy way to get eclipsed. The cool thing here is you don't actually need to be fully eclipsed. You can be partially eclipsed because even if you're partially eclipsed, it increases the latency for block propagation or message propagation. So for example, in Tezos, if you're not very well connected, message propagation may take a long enough time that people will assume that you're offline, even though your message eventually gets there. Okay, so the most technical of the attacks is probably ASN hijacking. So this sort of goes back to how the internet was constructed, and in sort of the 70s, 80s, we had a few large institutions that almost had direct connectivity with each other. But as the network expanded, direct connectivity really doesn't work, so we need these multi-hop message routing systems where I can be at my server, like in Switzerland, can send a message to a server in the US, but there doesn't need to be a direct connectivity. It can sort of hop between routers across the global internet. And this requires sort of people that are allowed to have IP addresses and own IP addresses are called autonomous systems, and they each get an autonomous systems number. But because it was built at a time where no one thought about sort of malicious activity, this is fully unauthenticated. So if I'm an autonomous system, I literally just broadcast which IPs I route. So if I know that validator A sits behind IP X and Y, and I have an AS, I can just start broadcasting that I now route for those IPs. And the routers will just accept these AS, like, unless you're trying to attack like large organizations that do have some protections around this. But if you start just trying to attack a small provider, other routers on the global internet will start routing the packets destined for validator A to you. And now you have the choice. Do you either drop those packets? Do you delay them? Sort of, you can't change them, but you can sort of fuck in almost arbitrary ways. It's almost like a remote man-in-the-middle attack without ever having to like plug into the network connection. This is a really cool attack. And we've seen this sort of happen on Bitcoin mining pools where people hijack the IP addresses where the local miners would connect to so that I could hijack their IP addresses and then point all the hashing power of that mining pool to my own nodes so that I would start getting the rewards instead of the mining pool operators. And we'll sort of see this as well, I think, in proof of stake at some point. The next technical attacks evolve a lot around censorship, and they get easier if you use sort of the previous tools. So the idea with censorship attacks is to cause validators liveness issues. So if I have sort of a full eclipse of a validator, I can just decide to turn it off, and all of a sudden that validator isn't online anymore, and no one else receives messages. I can start delaying the messages, so it just seems that he's like temporarily eclipsed. In protocols, so this also depends then on the exact protocol implementations, and I'll give 2 examples in Cosmos and Tezos. So in Tezos, this can be used to, if I start censoring people, like how people's newly created blocks get propagated, this can be used to decrease their efficiency because getting rewards in Tezos is directly linked to you signing a block. So if you you assign slots, and if you miss your slot, you don't get a reward for that slot. And you also have the concept of stealing. So if I have the second priority to bake the same block, and I then delay your block, I will get less of a reward, but your reward goes down and my reward goes up. And it's sort of, you can do this very targetedly, where you just target specific validators that you want to fuck with. And you can maybe like get a 10% drop in their efficiency and their rewards. On Cosmos, this works slightly differently because in Cosmos, rewards are socialized, meaning that you sort of have to participate in more than half of the last 40,000 blocks. But if I can get you to miss 21,000 blocks of the last 40,000 blocks, the consensus assumes that you're not online anymore and unbonds you. And sort of places you in this jail where you can't participate in consensus for 2 days. We'll come back to this later in the social cartel attacks, but this is a quite interesting feature that you can use to take over an entire network by dropping people from consensus. And yeah, so the last thing I want to talk about on the technical side is host compromise. And this effectively just means that as a proof-of-stake validator, you have some cryptographic keys on some machine, and that machine has to be somewhat connected to the internet in order for that key to produce signatures that can be relayed to everyone else. The problem is most people will just run with file-based keys. So if I ever just get access to the machine, I can exfil the key, and now I can cause a safety fault for that validator, so I can get that validator slashed. But from a whole network perspective, this is actually a terrible thing, because if I sort of in secret amass enough of these keys and exfil them or gain permanent access to them, I can start tricking full nodes and light clients, right? Like imagine if I sort of got more than 2/3 of the keys used in the Cosmos Hub, I could start lying to full nodes about the history, or like about whether transactions happen. I can almost create an arbitrary history. And yes, there will be slashing involved, but still this is like not a great idea, especially if you have light clients, and hopefully most of our mobile phones will actually be running light clients for these blockchains, because this is like one of the very nice features of proof of stake. Light client verification is extremely cheap and efficient, and light clients are even easier to trick. So there are 2 things you can do against this, and both involve HSMs. So one is sort of a standard HSM, such as a UB HSM. That does protect you against key exfil, but it doesn't protect you against someone maliciously accessing a host and causing a double signature. The cool thing, though, is that we have nano-ledger S's, which are extremely cheap HSMs, but which are programmable. And so I can write, and this exists for both Tezos and Cosmos, we can build ledger applications which verify the slashing conditions. So in Tezos, I have a ledger application that verifies that I never sign a lower block height than I previously signed, which means that even if all my servers get compromised, unless someone at the same time also manages to break into the ledger over the USB connectivity, that attacker can't physically cause me to double sign, which is something magical when you think about it, right? I can give an attacker full access to every server in my infrastructure, and that attacker can still not cause a safety fault on my validator. So this also exists for Cosmos. And there we track 3 integers instead of 1, because sort of the consensus is different. It's using Tenement Core. One interesting extension for HSMs in the future is to include time crystals in them. So most HSMs are really designed to sign as many things as fast as possible. This isn't like super useful in the blockchain context. I know like I have to provide a signature every 30 seconds. Why would my HSM be ever capable of producing a signature more than 20 seconds? Because if I have a time crystal, it ensures that an attacker can't sort of connect to my machine, create 100,000 signatures for my entire history and get me slashed due to this. They can only create signatures at a rate limit, at some rate limit. Okay, this was technical side, and I'm sort of going to speed this slightly up because, so yeah, I'm starting to run out of time. So social attacks against validators and proof-of-stake networks. These may involve some modifications, but usually they're more heavy on sort of the coordination side of large amounts of the network assets rather than large modifications of the code bases. So probably the easiest social attack is forming cartels, and cartels in proof-of-stake are terrifying. And I will say this now, there may be an argument for why it makes absolute sense to form a 1/3 defensive cartel at launch. Like if you're a rational validator, there may be a very good argument why you should immediately form a cartel because the only way to defend against a 1/3 cartel is another 1/3 cartel. And I'll sort of highlight why this is. So in Cosmos, if you have more than 1/3 of the network, you can start to arbitrarily, and by the way, I'm not highlighting Cosmos here as a specific, I'm highlighting as a specific example, but other networks are susceptible in the same way. I've just worked a lot with Tenement consensus before, so that's why I know the specific example quite well. So if you have more than 1/3 of the voting power in the consensus, you can start to arbitrarily censor people. And I mean, if I have 34% of the voting power within the network, I can say that I never let any pre-commit of validator A into the chain. I never let any transaction that increases the globally bonded stake into the chain. And so this gives me the ability that once I have 1/3, I can start to targetedly drop other validators from consensus. And so if this allows me to go from 1/3 to 2/3, at which point I control the entire governance process and I control sort of what everyone in the network sees. And depending on your slashing conditions, this may actually happen quite fast. Sort of in Game of Stakes, which we ran, this could happen in less than, I think, 40 hours. So if you have like 1/3, it's less than 40 hours to get to 2/3, at which point you own the network. And the only defense against this is to, at that point, hard fork. This is what I'm saying, that you may want to form defensive cartels, because the only effective way to defend against a 1/3 cartel is another 1/3 cartel, sadly. Even if you don't get to 1/3, that's fine, because you can start leveraging the technical attacks from before to sort of, let's say you have 10%, and then you start DOSing specific validators, so they start dropping from consensus. You're starting to eclipse them. You're starting to target them in any other way, and you sort of slowly grind your way until you have more than 1/3. If you sort of don't want to go that extreme, you can also just form soft cartels, which offer priority transaction inclusion, so that effectively, if you pay this cartel out of band, they will include your transaction a higher priority than would normally be the fact. Yes, there's also this concept of information asymmetry, which we've seen a lot, again, on the public testnets, because most validators spend very little time actually understanding the code base that they're running. And most people will just run whatever command like any reasonable person tells them in a Riot chat. I will give you this specific example from Game of Stakes in Cosmos. A bunch of people were running with UBHSMs, and which at the time seemed like a cool idea because it was like the first HSM that was available. But I sort of audited the code base there, and I knew that if you ran with the UBHSM with the current software version, you didn't have any double sign protection, not even accidental one. And so at some point there was DOS attack, the chain halted, and to restart, people started recommending to just delete consensus state.wal files, which a bunch of people did, and it's a miracle that no one double signed you to this, because the consensus state.wal files track the latest, so the consensus state that Tenement Core knew about, and if you just like randomly deleted it, there was at least a chance that you double signed because the HSM itself provided no protection against this. The other thing, which I think a lot of people underestimate, is do validators actually validate secure like patches to the software? Do you actually audit the code you're running? Because if not, you're only as far as like if the core team ever decides to, if you just download the code from the core team, if there's ever a malicious commit that goes in there, which is like not totally unreasonable to assume that it will happen at some point, even just by accident, you're sort of opening yourself up to a whole class of attacks there because you're effectively just running untrusted code even though it's open source. Another interesting information attack is what happens if you start posting illegal content into the chain that is specifically illegal, more so in some validators' jurisdictions than others, right? You could ostensibly imagine that pornography is very much frowned upon and illegal in some parts of the world. What happens if sort of users, even users of the chain, start uploading links to pornography into the chain? Can validators in those jurisdictions still continue, or do they have to take down their nodes? Will they be liable for distributing pornography? Who knows? Generally speaking, it is much easier to target proof-of-stake validators than proof-of-work miners because generally proof-of-stake validation is sort of this reputation-based game where you have to, where most validators are fairly public about what they're doing, so they're slightly easier to target. And this is not necessarily a bad thing. This is also a good thing from a sort of like assurance perspective that you know who's securing your network, but it's something that people need to design their protocols around. And sort of the last point on social attacks is governance. I mean, at the very simple level, you can start purchasing votes through smart contracts in governance. But sort of the more interesting attack is you can actually crowdfund attacks, right? So given that, that individual chains understand how to slash for safety faults, right? Like Tezos understands what a double signature is on Tezos, and Cosmos understands what a double signature is on Cosmos, and Polkadot understands what double signature is on Polkadot. Other chains can do the same. So as Tezos or as Ethereum or as Cosmos, we can start, like that governance system can start offering inflationary rewards to people that fuck with other chains, right? Like I can say that we will print 0.1% inflationary tokens for you if you manage to compromise more than a third of the Cosmos validators. This is totally feasible if you have smart contracts, or if you just want to build this in protocol. The other cool thing is we can sort of crowdfund attacks. We can start issuing tokens that only get their value once an attack is executed successfully. So an attacking team can issue this token saying, we will compromise more than a third of the Cosmos validators. If you buy this token now, you fund us. And once we successfully compromise it, the protocol pays you a reward, and that reward goes to the token holders. And you can even make this tradable. So the other cool thing is you can do this for protocol upgrades. So you can incentivize people to build new software for you by issuing the same kind of token strategy. But you can also use it for attacks. And yeah, I think generally we should just be very aware that in proof of stake we can heavily incentivize, like chains can attack other chains. And this is mostly a social game where you try to convince sort of the governance mechanism of your chain to pay for attacking another chain. This may be quite controversial, but that's why you have on-chain governance. As the last thing I want to talk about is just safety versus liveness trade-off. This is sort of on a side. A lot of testnet communities and sort of project communities, validators care very much about liveness. So they sort of have these fancy diagrams that explain their Sentry node architectures and like how they have fully redundant setup. They have like keys in the US and the UK, and if one of them goes down, the other one automatically comes up. Let me tell you that from experience, this is a terrible security model. Mostly, so as a story, on Tezos, this is how all the slashing has happened. There were 130 slashing incidents so far, and effectively all of them came from validators that had automatic failover solution. So they replicated the same key on 2 servers, and then sort of the hacky ones had a shell script that sort of determined, is the first node still online? If not, spin up the second node. The shell script failed, and all of a sudden you had 2 nodes signing at the same time. Fancier validators will call this the coordinating server. It's still effectively the same thing. It's a single point of failure, where if that coordinating server fails or a shell script fails, you're double signing. The other thing is now you all of a sudden have this toxic key material in multiple jurisdictions. You have to sort of travel with key material. You have now an increased physical attack surface against duplicated key material. So generally speaking, not a huge fan of people that replicate keys for redundancy, because in most protocols, safety for good reasons is punished much harsher than liveness. So it's much more acceptable to go down for a day than to double sign. Like going down for a day costs you maybe $500, double signing may cost you $30,000. Like those two stand in no relation to each other in my mind. Yeah, anyone that claims that they have the perfect system that is as safe as possible while also being as live as possible most likely doesn't understand that there are inherent trade-offs between those two. You can't have perfect liveness and perfect safety. And I think the reason why a lot of people focus on this liveness aspect is because that's what we're used to, right? Like, this is how we build web service architectures for years. It's always about automatic failover. If one of your microservices die, you spin up a second one. Let's put everything in Kubernetes, and this is going to be awesome. It will never be down. In blockchains, and especially proof-of-stake validation, this is really not the model that we're building, that these systems are built for. At the same time, sort of having, for example, the Sentry node architecture actually introduces extra latency, right? So I think there's fundamentally a story around you should run validators with with security features that cannot be retrofitted. So once your server is compromised and you have a file-based key and that key is exfilled, you cannot then upgrade to UBHSM to prevent this. Once your server is compromised and the UBHSM created a fake signature, you cannot then upgrade to Ledger S to validate this on chain, to validate before you get a signature. So there are some things that you cannot retrofit. Things like Sentry nodes and liveness features, you can always retrofit them. It takes 3 seconds on Google Cloud to set up 50 Sentry nodes. So if you're actually being hit by DOS, just like spin them up then. There's no point in sort of trying to isolate yourself behind this massive firewall, because it really doesn't buy you anything for the usual network operations. Yeah, so generally focus on those protections that you cannot retrofit and sort of just be ready on standby with those things that you can easily retrofit, such as Sentry nodes. Yes, so in conclusion, validators are the security backbone of all proof-of-stake networks. And don't design protocols without thinking about how they will be secured, right? Like if you're building your own blockchain and you're building your own proof-of-stake implementation, make sure that you give people the ability, at least, to run secure validators. You don't have to tell them exactly what to do, but provide the tools in order to enable this. And yeah, if you don't, then no one will run them safely, and overall, the network isn't going to be secure. More so, you need to incentivize people to run safely, right? Like, there needs to be some slashing, and things like EOS I call unreasonable because there's no slashing. Like, in EOS, the best strategy as an individual validator is to run on a cloud instance somewhere to replicate the keys across 500 instances, because there's no punishment for if you double sign. There's only punishment for if you go down. So if you care about security of these systems, build systems that incentivize people to be secure, not to be instead of focusing fully on liveness. Yeah, generally speaking, most successful attacks lie at the intersection of the technical and the social attacks. And so like pulling off a purely social attack is difficult, pulling off a pure technical attack is difficult. If you can figure out how to combine both, you have very good, there's very interesting things you can all of a sudden do. And generally speaking, don't think that someone will somehow figure out how to secure your network. Securing a network isn't a trivial task. It's a really complex operation that requires dedicated resources. So when you build these systems, really think about how you want them secured and design for it. And sort of as the last thing, as a community, I think across networks, we need to be way more adversarial, right? We want to test how these systems work before a malicious external actor is trying to attack us, right? If we aren't adversarial to ourselves, the first real attack that hits any of these networks will take them down because we never tested the security assumptions or how we secure these networks. Yeah, thank you very much. And if you have any questions, I'll be around later, or maybe I have time for one question, I think.